Oh, well, thank you, Steve, and hello, everybody. This was the little talk I was supposed to do in February, but a little snowstorm scared me away. so, um, so this is, Steve mentioned, this is a book that kind of gave me some ideas of some things to talk about. There are some things that I learned a lot, and I've just selected 4 subjects in the book. And just before I get going, it's just a reminder, it's called Cosmos, the Infographic Book of Space. And there's a lot of information. It's got 9 chapters and 100 different sections. Now, they're not big sections, but each one has a little bit of different types of information. And it's available online as well. So if you just Google the title, Cosmos, Infographic Book of Space, you can go onto the website, and there's a few of the sections that are activated, so you can go and try them out for yourself. And so it's pretty cool. So I'm not doing a book review. I've just used the book to kind of give me some ideas of some interesting things to go over. So the 4 things tonight are, how many planets are there in the solar system? And I didn't realize this, but this number has changed a lot over the past several centuries. The second topic is Catch a Falling Star, and it's just a little information about some of the objects that are in our solar system that are different sizes. Some of them hit the Earth, and some of them come very close to the Earth. Another little section I thought was cool was how high can you jump on different bodies in the solar system? And there's a little, if you go onto the website, there's a little graphic there that you can actually jump, and you can see how long it takes you to jump up. And it also gives the same information for a kangaroo. Kangaroos apparently can jump even higher. And then I'll finish off with the We Are Stardust section, which is about the different chemical elements that are found in the universe and where they come from. Okay, so the first one is, how many planets are there in the solar system? So this number has varied a lot over time. And I guess it comes down to what is a planet. So way back sort of in the old days, before the telescope was invented, it was believed that there were 7 planets in the solar system. And at that time, the sun was considered a planet. The moon was considered a planet. The Earth was not considered a planet. And this was something I only discovered recently, was that the 7 days of the week are named after these 7 solar system objects. I guess some of them, Sunday, kind of makes sense that that's the sun. But I just didn't realize that, all of the different objects like Mercury, Venus, and Mars all went into the names of the week, which I thought was very cool. I'm sure most of you here already knew that, but it was just new to me. And then Galileo came along and turned the telescope to the sky. And as many of you know, he discovered 4 new moons orbiting Jupiter. And on that very night, the number of planets in the solar system jumped up to 11. And then it was Huygens' turn later on when he pointed his telescope towards Saturn and started discovering things orbiting Saturn. So when Titan was discovered, the number of planets went up to 12. And then Iapetus was discovered, up to 13. And then Rhea makes it 14. A couple more moons were discovered in 1684. And at this time, there were 16 planets in the solar system. At least that's what they called them. And then, and that lasted for quite a while, almost a century. And then in 1758, a person came along who made a very important discovery. And in doing this talk, it dawned on me how important that discovery was. Edmund Halley had successfully predicted the return of Halley's Comet, or what would become Halley's Comet. And that changed everything. It changed the understanding of what comets were. It changed the understanding of what the solar system was, the objects that comprised the solar system. And people just started asking some really hard questions, like, what are we actually seeing up there? And they said, wait a second, the sun is not a planet, it's actually a star. The moon is not a planet. It goes around the Earth. It's like a satellite, you know, and so they kind of started realizing this, and the objects that were going around Jupiter and the moons that were going around Saturn, these were also satellites. So they started kind of making some more rigorous definitions of these things. So in that 1 year, we lost 10 planets, apparently, if you just look at the numbers. So when Halley's Comet returned, we went down to 6 planets in the solar system. And then a few years later, William Herschel discovered the planet Uranus. The number went up to 7. And then we started discovering some other objects. And this is when Giuseppe Piazzi discovered Ceres. And at the time, Ceres was considered a planet. 8 planets. Then Pallas was discovered. We're up to 9. Juno was discovered in 1804. And then, as Jim pointed out tonight, Vesta was discovered in 1807. We're up to 11 planets. Then another very important discovery was made. I forgot about Astrea. Up to 12 planets. And then in 1846, the planet Neptune was discovered. And they realized that Neptune and Uranus were different than Vesta and Juno and Ceres and Pallas. They knew that these objects, the Vesta and Juno and Ceres, were close to the sun because they were moving much more. Their path through the sky was much faster than was the path of Uranus and Neptune. They realized that Uranus and Neptune were much farther away. And when they started to discover more of these objects, they kind of went, wait a second, these really aren't planets. So from 1847 to 1829, the number of planets actually went back down to 8 again. They realized that these objects that were orbiting between Mars and Jupiter were not really planets. They looked like stars, but they weren't really stars. They were star-like, and so they called them asteroids. So you can see how this progression of learning more and more as time goes on, and it's a process that can sometimes take multiple lifetimes or centuries. So it's interesting when you look at the sky and count the number of planets. This number took a long time to come down to. And then, here we go again, 1930, Clyde Tombaugh at the Lowe Observatory discovers another object. And he knows it's way out there. It's a long way out there. They named it Pluto. So it's out beyond Neptune. And it looks like it's a planet. But then in 2006, they're starting to discover, just like they did with asteroids, a lot more of these objects. And they're like, wait a second, maybe these aren't planets. And so they had a meeting, and as we all know, Neptune was kind of booted out of the Planet Club. But it's called a dwarf planet now. So Pluto has sort of a special status. It's a planet, but it's a dwarf planet. And there's a number of these dwarf planets out there, including Ceres. And when I put this talk together, the latest information I had was that there were 5 official dwarf planets, but as Jim pointed out tonight in the Astro News, there may be hundreds now. So, and that just means that we're discovering things all the time, and the number of planets may change yet again. So that's that topic, which I thought was kind of interesting. And this is a little shorter section here on some of the objects that are in the solar system that have either collided with the Earth or come very close to colliding with the Earth. Probably one that we're familiar with is the Tunguska event, which occurred over Siberia in 1908. They believe that the object got as close as 2 kilometers and then it vaporized about 2 kilometers above the surface of the Earth. And it was big. It was about 85 meters in diameter, they estimate. And I believe they estimate this by the damage that it did, the size of the blast zone. They kind of figured out its speed and its size, and they had different techniques to kind of work out just how large this object was. And how fast it was going when it impacted the Earth. And the thing is, it actually didn't impact the Earth. It blew up before it hit the Earth, but the blast was pretty impressive and was enough to level quite a large area of forest. And more recently, the Chelyabinsk meteorite in Russia in 2013, a much smaller object, but big enough to shatter windows. It's estimated to be about 17 meters in diameter. And a still smaller object collided with the Earth in 2008, and it was about just under 2 meters. And there are platforms now, observational platforms, that are starting to look for these objects and figure out where they are, trace their orbits, and see if they represent a threat. Here are some of the close approaches. So the black table, the table with the black letters, these are objects that have already passed the Earth. You can see a few of them are pretty big, 40 to almost half a kilometer, over half a kilometer in diameter. But when you look at the closest approach info, they really don't get terribly close to the Earth. Duende came fairly close, 34,000 kilometers in 2013. And the large one in 1925, it was big, but it was like 26, almost 27 Earth diameters away, so still pretty far. And there's a few in the future that are a good size that are predicted to come fairly close, as close goes. But even the closest one, Apophis, will be 2.5 Earth diameters away. That's still getting pretty close. It's kind of like standing in a room and somebody's gonna shoot an arrow that's gonna go, 2.5 head diameters away from you. So it's a little bit nerve-wracking. But so far, there's nothing that's predicted to collide with the Earth. So, and a little thing here that I thought was interesting, I did a little research and found another paper by this author here. And I wanted to see how many different objects were out there of different sizes and how many of them are impacting the Earth. So this paper predicted that there's objects between 10 centimeters and 1 meter in diameter. They estimate there's 127,000 of these impacting the Earth every year. They're fairly low mass. Their velocities are not that high. And the energy equivalent is not that much. So these are the bright bolides that we might see. And there's a few that are even larger that are between 1 meter and 10 meters. And it's astonishing. I was like, I couldn't believe the number that there's 2,800 of these impacts a year. But again, they even though they're large, these objects are not terribly massive. A lot of them are composed of ices. So like methane ice or ammonia ice, and volatile. So they're not very massive compared, like they're not like stony iron meteorites per se. But I thought that was quite interesting. So, and just to conclude here, I thought it was interesting just to chat about this Chelyabinsk meteorite, which occurred about 7 or 8 years ago. So from the numbers, they figured, like I mentioned, at 17 meters diameter. It sort of entered into the Earth's atmosphere moving at 19 kilometers a second, but as soon as it starts interacting with the atmosphere, it slows down, and it slows down by quite a bit. And it was quite massive, big mass, like it's like 10 million kilograms, and 440,000 tons of TNT. That's the energy equivalent. And it was fairly dense too. But even so, that's, given this, even though that's the size of that object, it basically, like I said, it shattered a few windows and a few people were injured, but that was pretty much the limit of the damage that was done, even though it seems like a fairly large object. And in order for, and it didn't, I don't think much of it reached the ground. There were a few fragments that reached the ground, but there wasn't a large object that reached the ground because, again, it was not like a big chunk of metal. It was like this, it was like a big piece of sponge toffee. You know, there wasn't much to it, and it tended to vaporize before it hit the ground. And in order for it to actually create a crater, it has to be moving at a speed greater than 4 kilometers per second, which I don't believe it was doing. So, and this is that other asteroid I mentioned that's due to pass the Earth in the future. I forget the date, 2029, I believe. And it, like I mentioned, it'll come within 2.5 Earth diameters. No, that was a different one. Sorry, this is the asteroid Bennu. Did I have here? So we probably heard of that NASA Near Earth Observations Program, or the NEOP program. They've mapped 20,000 of these objects so far, and tracking 8,000 of them. And in spite of all of the different objects out there, there's no collisions predicted. So there's really, you know, we kind of know how huge space is, and that it's mostly empty space. So it's really, it's not a huge surprise that there's nothing big that's on the horizon like that. But plenty of bolides to see, and brighter objects if you happen to be in the right place at the right time. And this section I thought was kind of cool. And if you go onto the website and have a look at this, this graphic that they have, you can go in and select if you want to be like a human being who's jumping, or if you want to be a kangaroo. And you can choose from several different objects in the solar system. You can choose the Earth, or you can choose Jupiter, Saturn, some moons of Jupiter, or even Phobos, which is one of the moons of Mars. All different masses, and you can sort of see how long it would take you to jump into above the ground and then land down again. And the numbers vary quite a bit. So here's a little table I did showing, you know, on the Earth, the average human can jump maybe 0.6 meters, or a couple of feet into the air. A kangaroo can get quite a bit higher. They can go almost 6 feet into the air, or 1.8 meters. And you can see the difference on the moon. You can jump quite a bit more on the moon. And so it's interesting when you look at the old Apollo footage of the Apollo astronauts on the moon, you can tell that they're jumping pretty good, but those space suits that they had, the suits they were wearing were really heavy. They weighed several hundred pounds, but on the moon they weighed 30 pounds. So it weighed them down quite a bit, but so they couldn't jump up as high as we can on Earth, or would if they didn't have a spacesuit on. But I thought that was kind of cool. Venus is very similar to the Earth in terms of mass, so there's really not a huge difference there. And then the big planets in the solar system, no surprise, we can't jump very high on there. On Jupiter, we'd be lucky if we can get just a few centimeters off of the ground, assuming you could find solid ground on Jupiter. There really isn't a solid surface there, but assuming there was. And going to some of the smaller objects in the solar system, you can sort of see here how high, if you were on these objects, you could jump up into the air. And I kind of am interested in the last object there, Phobos. Phobos is not that big. It's a small moon of Mars. It's about 22 kilometers in diameter. And its mass is not much. It's about 24 times the mass of Mount Everest. So it's really not a very massive object, but it's big enough. It does have a gravitational field. And if we ever send someone to Phobos and they happen to jump, they will jump 850 meters above the surface of Phobos. And it'll take them 9 minutes to get to the top of the jump, and then another 9 minutes to fall back down. So I thought that was kind of cool. So that's one of the things you can check out on that graphic there. Kind of cool. And finally, the last topic here. This is one that's kind of close to my own heart. It kind of reminds me of Carl Sagan, that wonderful episode that in Cosmos that he spoke about all of the elements. Remember the one that starts off with he goes, in order to create the universe, or in order to bacon apple pie, you first have to create the universe. I love that opening, and this reminded me of that episode. And I thought it was very interesting because I learned a lot of it. I learned quite a bit about the where the different elements in the periodic table, where they come from. So this is that's a big table. There's a lot of information there. There's a lot of different elements. They go all the way from hydrogen, element number 1, all the way up to element 118, that oganesson, which was recently discovered. So I thought we'd go through that and just sort of see where they come from. So, but first, these ones that are highlighted in pink, these are the elements that are considered essential for life. So I'm going to kind of make sure these are all highlighted in here, just to see where these elements, where they come from. Like, for instance, like a lot of these heavier elements that like molybdenum and copper and zinc, a lot of these elements are really important, and manganese are important in different processes involving amino acids in the human body. And so you may not use very much of them, like selenium. Selenium is not used very much, but it's essential for life. So we'll probably realize that when the Big Bang happened at the very beginning of the universe was created, it created all of the hydrogen in the universe, and a fair bit of helium, and a tiny little bit of lithium too. And stars like our own sun that are fairly low mass, and by low mass, I mean stars that are not massive enough to become supernova. They basically end their lives as white dwarfs and planetary nebula. A star like our sun. And as it goes through its main sequence phase, which is about 90% or more of the life of the sun, it will create, it will fuse hydrogen into helium. Helium will be fused into other elements like carbon, nitrogen, and oxygen. And apparently lithium is created in this process as well. But you'll notice there's no beryllium or boron created. So stars like the sun don't create beryllium or boron. But then when a star that's when a star the mass of the sun, when it dies, it creates quite a chemical soup of elements, which I didn't realize. I didn't realize that. It doesn't create any of the elements on the 4th row of the periodic table that go like from potassium all the way across to krypton, none of those, but it creates heavier elements. And it does this through these different processes. They have some names for them, something called slow neutron capture. And this is in the phase of the final phase of the sun, when it's in something called the asymptotic giant branch. That's when it's really exploding, and not exploding, but expanding and becomes a red giant and gets quite large. And there's quite a lot going on in the interior. And these different processes create elements quite heavy, all the way up to lead, which I was quite surprised at. So that was news to me. Maybe a lot of you knew that, but I had no idea. Now the massive stars. The massive stars, this is something that I was aware of, that massive stars create elements all the way up to iron, and they even go a little bit beyond that. And so that was news to me. I didn't realize that cobalt and nickel and copper were created as well. And for some reason, zirconium, element number 40. Unfortunately, the book doesn't explain, it doesn't explain why zirconium is created. It just indicates that it was. That's another mystery. So this is during the main sequence phase of the massive stars, creating all of these elements. And of course, if you look at a star like Betelgeuse, which is it's nearing the end of its life, it's going through the fusion stage. Hydrogen is fusing into helium. Helium is fusing into carbon, into oxygen, neon, magnesium, silicon, and then finally iron ash at the end of it. And the timelines for these are interesting too. So Betelgeuse fused hydrogen to helium for 10 million years. And then helium was fused into carbon for about 1 million years. Carbon will be fused into oxygen for about 1,000 years, and oxygen into silicon only for 6 months. And then iron, that takes place in less than a day. In fact, it may be only like minutes. It's very short. And just a reminder, so stars that have cores that have 1.5 times the mass of the sun, those are predicted to become, or have the possibility of becoming supernova. And as soon as iron is created in the middle of the core of the star, that's the end. That spells the end. The star goes supernova. So when it does go supernova, another range of elements are created. Again, not quite as many as I thought. We go beyond copper all the way across to the end of the 4th row up to krypton, and then up to yttrium. And then nothing's created. So here's where I thought supernova explosions created gold. Apparently, to this new information, they don't. But they will create thorium, uranium, and plutonium. And then when you get something as esoteric as a merging neutron star, so here we have 2 neutron stars orbiting each other, and as their orbit decays and they spiral into each other, this creates another host of elements that are being created. And this is one where gold is created. And all the way up to to plutonium, element 94. And this answered the question of where beryllium comes from. Beryllium, and this was new to me, I didn't realize this. Beryllium is an element created by a radioactive decay. Even though it's element number 4, it's the 4th lightest element on the periodic table, or the 4 protons. Relatively simple compared to all of the elements above it. Yet stars can't make it. Stars, whatever processes happen in stars, they cannot make beryllium. So that explains why beryllium might be so scarce. And this is the final slide here. These are isotopes, or sorry, not isotopes. These are elements that are created artificially. They're created in particle accelerators and by colliding certain isotopes of different elements. They pick sort of elements that add up so that the numbers of protons and neutrons add up to give them sort of what the element they're trying to create, and they smash them into each other. And if they're lucky, it will exist long enough that they can confirm that it exists. So for instance, that element 118 at the bottom left of this, near the bottom left, element 118, that oganesson, it existed in a particle accelerator for less than a second, but that was long enough to confirm that it existed. So these highlighted elements, there's no stable isotopes. They do not occur in nature. They only, as far as we know, exist on the planet Earth in very specialized environments. So, and this is the second last slide here, and then I'll be finished my talk. And I thought this slide was very interesting. It's a graph that shows the relative abundance of the different elements on the periodic table. And you can see if we start at the top left of the graph, I have hydrogen and helium circled. And then you can see the relative abundance is the axis on the sort of the y-axis there. And along the bottom, that axis is the atomic number. So as we go to the right side of the graph, the atomic number increases, the number of protons in the atom sort of increases. In fact, till we get to at the bottom left, so bottom right of the graph, we get to uranium, which is element 92. So everything's sort of relative to uranium. So, so we have, for every one uranium atom, we have like more than 10 to the 12 hydrogen atoms kind of thing. And you can see the numbers kind of go up and down. And in beryllium, element number 4, you can see it's really not abundant. But when we go back up to carbon and oxygen, you can see that carbon and oxygen are many, many orders of magnitude more abundant in the universe. And good thing for us, because we kind of need those to live. And so carbon and oxygen. And another interesting thing, you'll see that the abundance kind of zigzags. It kind of goes up and then it goes down. It goes up and down. So for instance, oxygen is very high, then it drops down to fluorine, and it goes back up to neon, and then down to sodium, and then up to magnesium, down to aluminum. And that's because the peaks of those valleys are atoms that have an even number of protons. And the valleys are atoms that have an odd number of protons. And as some of you may know, that a lot of these these fusion reactions that are occurring in stars involve the element helium, which has 2 protons. So when a helium atom collides with one of these atoms, they just get 2 extra protons. So that's sort of believed to be one of the reasons behind why even numbered elements seem to be more numerous than elements that have odd numbers. But yeah, so that was kind of cool. And yeah, so except for hydrogen, helium, and a tiny bit of lithium, every atom in the universe was, in one way or another, forged inside of a star, including beryllium, because in order to make beryllium, you have to have a radioactive isotope, and those radioactive isotopes are made, like uranium or radioactive thorium, are made in the interior of a star. So that's that. So yeah, so thank you for your attention.